Okay, let me start. I mean, there is some. Okay, so you can all hear me, right?
Yes.
Okay. Please move on. Yes. Yeah. I mean, I'll talk about project definition and task a little bit more. Once Diganta joins. Okay, but one thing that the project will have you do some verification task, a set of verification tasks on a bunch of tools. Okay, so what those things will be and etc. will be defined more clearly. But as a warm-up assignment, I'm saying that this is something that we want each of you to be working individually, and I'm thinking want to assign maybe 15 to 20% of the project weight, um, project grade for this effort. So to ensure that you do get acquainted with the tool, at least some of the tools that I think maybe Diganta is here. No, not yet. Okay. I don't know what's happened. So first thing is, see this ACAS network, I don't know if you had a chance to look at it, it has some 45 different neural networks. They're all, you could say that they are implementing this flight guidance control for different scenarios. Okay, for each scenario, it uses a different neural network. And then it has a whole list of properties. Some of them are safety properties and some of them are robustness properties. Okay. And then, some of them probably make sense for only some of the scenarios, and so maybe there may be some properties that make sense for all the scenarios. Okay. Diganta is here.
Yeah, I'm here. Sorry for being late.
Okay. So what shall I do? I mean, shall I go through just this the warm-up?
Yeah, sure, sir. You had started, so maybe.
Okay. So the first warm-up thing is, we want you to make sure, we want to make sure that each of you gets started on it early on. And this one, that's why I'm assigning this, and this will be kind of due in a week's time. So we want you to be not push it till the end. First thing is, we want you to simulate the network. I'm saying TensorFlow here. Maybe Diganta, you can chime in as to what exactly you want. I mean, we want you to get acquainted.
Yes.
With
in terms of simulating the network, either TensorFlow or PyTorch would be fine. But yeah, so there is some complexity regarding the networks are in a particular file format, so you have to read and parse them and such things. But yeah, so you can use either TensorFlow or PyTorch or whatever you want to simulate it. That is okay, I think.
Yeah, but you'll have to generate some input to it, no?
Yeah.
Which you'll have to, okay, maybe you could do that in TensorFlow or.
Yeah. I think TensorFlow, PyTorch, or NumPy for all that. Like even pure NumPy will should be enough to generate those inputs. Yeah.
So what I have left it to you to choose, one or two of the 45. I mean, for you individually, okay, and maybe pick some 3 properties from the list. I haven't looked at the list of properties. Maybe you can, go over it, Diganta, if not today, at some point. And these are left to you. I don't know. Do they have? I'm assuming that they have some properties which could be considered just safety properties. Something bad should never happen, and the other properties which say that whenever something good happens, that the same good should happen for some perturbation, like robustness. Do they have both kinds of properties?
No, so all of the ECA60 properties are kind of like safety properties.
Okay.
They don't have robustness properties. In this list of 10, there are no robustness properties as such.
Does it even make sense?
It might, but usually with robustness properties, it's with respect to some candidate inputs or or all inputs that the network was trained on and such. And those sort of things are not available here. So I think these 10 properties, the safety properties, are the one that makes the most sense.
Candidate input are not available for, those inputs for which it is, but these safety properties are meant to be proven for all inputs, correct?
Yeah.
Okay, they're all safety properties. Okay. But that's then can be, I don't know if there is any property for this kind of a system that makes sense, or maybe, even when it says there is no, it never allows 2 things to collide, you may want to prove something like even when it does not collide, you don't want it to get to within a certain, if you vary the input, then it won't get it very close or something like that. You could prove, no? Okay.
We can.
Within it being safe, you may want to allow for certain minimal margin. Okay, and at that you could see how it varies or something like that. So you could make certain robustness property. That probably could be done. Some of these kind of more interesting and what I call is not completely open-ended, something which has not been done. That is what we are including, that we are having to do as part of the project. Okay, and we can consider that. Okay, permutation invariance is a class of properties that we want to consider. Maybe if they're not doing any robustness properties, maybe you can consider robustness properties as well. But let's reserve that for the thing. So right now, as part of this assignment, what we want you to do is to pick any 3 properties. Okay, and maybe some of the properties, I don't know, maybe if they're only safety properties, then they should be they are relevant for all scenarios. Correct? Okay.
Yeah, so since the networks are sort of split according to scenarios, some of these safety properties have a precondition saying if such and such thing happens, then this should hold and so on, right? Yeah. So that often eliminates some of the networks.
Oh, I see. Okay.
So that is there. Other than that, yeah, it's applicable for all scenarios.
Okay. Yeah, I mean, I would encourage, you know, you to, I mean, although I've left it to you to pick what, you know, scenario that you want to choose, you know, maybe you want to let you know, people do, you know, don't just do all the same. So if you could have, if you know your friend is picking one, you may want to try another. Okay, but it's up to you. So simulation is one thing. Then you verify the chosen property and the chosen DNN scenario using ReluPlex under Marubu. Then you redo the verification by changing the property in such a way to make it fair. Okay. I don't know. For a safety property, it might not be possible, no? I don't know. Maybe you could change the input. How do they do that? Okay. Without looking at the property, I cannot. So the idea is to generate to do some change. Okay. Maybe you can change the input constraint. Okay. Something.
Yeah, so most of these properties have some tolerance value sort of yeah, constants which can be changed.
Okay, so that you could try to see how you'll get a feel for how counterexamples are generated, and you know, by Marubu, and that you will do things. So ignore the robustness kind of a thing. If they have tolerance, then you could change those tolerance, make it tighter, and see to a point where it might fail. Okay. That is something I want you to do as part of this assignment. Then you redo the verification using this thing called node merging heuristic. Okay, that I'll be talking about tomorrow. Okay. And another thing that I want you to do is to verify the same property using deep poly. Now, in deep poly, when you do ReluPlex, you're not using any abstraction. Okay, for 3 and 4, you're using some abstraction, and 3 uses abstraction refinement, and therefore it's a complete method. But when you do using deep poly, you're only using an over approximated abstraction. So you may, with the bounds that it generates, you may be able to verify the property or not. Okay, it's unclear, but that's what we want to do. The purpose of this exercise is for you to get your hands dirty with deep poly early enough in the project cycle. And you know, so what I'm having you do is to verify the same properties, the same property that you have chosen, to see if it the over approximation is tight enough to verify any of those properties. Okay, not having looked at the properties, you know, I don't know if deep poly can verify any of them. Okay, but that would still be, or maybe some property which are all bound kind of a thing, it may be able to verify. So, but it still would be an interesting exercise for you to see if there are any properties for which, for that particular scenario, that deep poly can verify. Okay, so those are some of the things that I want you to do, and I want you to get started, and I want you to finish it maybe by the end of this month. Okay, in 10 or 12 days. While you are also thinking about ways to do the actual project, about which the project task about which Diganta will be talking about. Do you have any questions about the assignment part? All are here. Let me check. Oh, Hardik is here as well. Someone is missing. Oh, Nabil is missing. Okay. I'll make you co-host and so Armdeep is here as well. Good. Okay, go ahead, Digata.
Yeah. So I'll just start. Yeah. So, so basically, the project that we want to do is based on this one particular idea of trying to find groups of neurons and treating them as a single activation function, and then seeing if we can approximate that entire group using Linsen.
But before you do that, I just wanted to add, see, the ACAS network, by the way, has already been verified successfully, in the sense all the properties that are listed and for all of the scenarios, they have been successfully verified with ReluPlex, as well as that node merging heuristics. Okay, the node merging abstraction technique is supposedly supposed to improve performance. Okay, when you do that, so it has already been done. What we are trying to have you do is something called a permutation invariance properties, which is slightly more complicated. Okay, for the reason that we will describe it, something that if you permute your inputs, certain properties get symmetrical and they get preserved, is what you're trying to prove. And one obvious way to do it is to increase the size. Okay, almost make 2 copies of the thing, and then maybe they don't scale as well. Maybe they do, maybe they don't. Even if they do scale, the idea of the project, the overall idea, is to use one kind of abstraction technique using Linsen. And that's what Diganta. So that's kind of the background, the motivation for why you want to use Linsen. Okay? With deep poly. Yeah, go ahead.
Yeah, so I want to just mention something very quickly before moving forward about deep poly. So the implementation of deep poly that is available most readily is a part of a tool called ARAN. So the issue with this tool is that this is specifically directed towards robustness verification. And one of the things that I looked into was whether we can use this tool, ARAN, and somehow get a better interface for it with which we can try properties other than robustness verification properties. And it seems like that is going to be a little bit difficult because it's all written in C, and going into the internals of that is kind of hard. So instead, if you want to run deep poly on some other some other kind of property than robustness verification, I think it's better if you directly implement it. And the implementation is not too hard, in the sense that all you need to do is keep track of some linear upper and lower bounds for all of the variables and compose them, right? All of that can be done with NumPy. So what I suggest is that we do this implementation. And we will probably have to do this as a part of our project at some point. So as a part of this warm-up exercise, you will have implementation of course, you'll get to know how to call ReluPlex and so on. You'll have an implementation of this node merging based technique that Sir will mention. And you will also have an implementation of this deep poly. So I think, yeah, so I think with all three of these things, we should be in a good place where we can try various things in the project.
Yeah, but for doing number 4, applying deep poly to verify some of the properties, they may have to do some programming. Isn't it? So is that what you mean? So because
yeah, they'll have to re-implement it because this ARAN doesn't have a very good interface for other kinds of properties than robustness properties.
Oh, because the properties have to be encoded as part of the thing, huh?
Yeah, and ARAN specifically expects robustness properties. So it won't really give you like.
But why would I would consider safety properties as kind of a special case of robustness properties, no? Because it's a degenerate robustness property in the sense the input does not change. The epsilon, the perturbation on the input is 0. The epsilon is 0. No, if you consider it that way, then why would?
Okay. So for example, if you want to say something like one of this particular output class is the highest. Yeah, I think that might be doable.
Yeah, but so what I would suggest is that as part of the warm-up assignment number 4 of deep poly, try a RAM, doing it under a RAM, and see if you can do it. Then maybe you can do it, but you may want to consider doing your own implementation in any case. Okay, so that you can shed some light on that. Yeah.
Yeah. So yeah, but I do feel that like eventually maybe doing an implementation might be beneficial for us.
Okay. Yeah, because you need more than we're trying to do more stuff, right?
Yeah, we're going to try and take this, combine it with Linsen and so on, right? So for that, I think it's best if we.
Yeah, but I don't exactly understand. I don't know if the others do either. What exactly you mean when you say read? You have to redo your implementation. Maybe.
So what I mean is that you'll have to implement the deep poly algorithm in something like Python.
Oh, I see.
Yeah. And
that means you have to implement deep poly like thing itself, like all that propagation and so on. Huh?
Yeah.
That should be.
Yeah, that is going to be some amount of work. Yes. Especially if they're also doing the positive negative, like the node merging based abstraction also is a part of this. So maybe let's do the node merging abstraction by the end of this week, and then we can look at deep poly in the next week, right?
Okay, so that we could do. Yes.
Yeah,
that can be done. So maybe that can be part of the project task rather than the assignment.
Yeah. Okay, so that having said that, here is basically
what they can do is to see if it can be done using ARAN itself. That if they want to do, then
yeah, that sure. That can be seen, but I doubt that will. Yeah, maybe that will work out. We can check that. So, right. So now the basic idea of the project is basically this. So suppose you have some network. Let's say that there are 3 inputs, and then let's say that we have 5 neurons here, 5 more neurons over here, and then finally let's say again 3 outputs, right? Now, if you look at what deep poly or even other methods they try to do is they try to come up with these linear bounds on the values of multiple variables together. So we want to find some linear bounds, and the idea with linear bounds is that they're amenable to things like LP solving and such. And we want to find them on multiple variables together. Right? So using both of these things, the idea is that with both deep poly and some other methods is that you can sort of create an over approximation that tracks relations between variables. Right? So what our idea for this project is to sort of take this one more step further. And the key in or sort of key. Hello.
Yeah, we can hear you.
Yeah, sure. Sorry. So the key idea of this behind this is to sort of consider these some groups of neurons coming from multiple layers as being a single activation function, right? Now I'll explain what I mean by this. So right now I'm separating these neurons into pre-relu and post-relu sort of values. Now consider a group of neurons that looks something like this. So okay, the input sides don't have any relevance. So the input is just some 3 values. So consider a group of neurons that look something like this. So you take these 2 input neurons, take 3 neurons from the intermediate layer, and let's take one of this neuron in the output layer, right? So consider this group of neurons. Just a sec, I think somebody is at the door. I'll just okay. Yeah, so consider this group. So then this entire group of 5 neurons is a function from R2 to R, right? Because it takes 2 inputs over here and it has 1 output over here, right? So the idea is that can we actually take this entire group and just replace it with some linear upper and lower bounds?
Diganta,
yeah.
One question. So why do you have these 2 dots with
which 2 dots?
No. You have 2 dots connected with an edge. So what do you
right. So this is before and after the relu.
That's all. Okay.
Yeah. So this operation is over here.
Yeah, it's just the value. Okay, fine.
Yeah. And of course there are your linear edges like this.
Yes.
And all of that, right? Similarly, you'll have edges like this. So if the idea is that if we can take this entire group of 6 neurons within this sort of blue region, so 2 input neurons and 4 intermediate neurons, this entire thing is actually can be treated as a function from R2 to R. And then what we can try to do is we can get linear upper and lower bounds for this entire region or entire
sub-region.
Yeah, function, let's right. And that will allow us to abstract this network in some way, right? So specifically how? So now once we have those linear upper and lower bounds, we will have converted our network into an abstract version where what we'll have is going to look like something like this, right? So this was the original network. And I'm not drawing the edges because it's a bit cumbersome, but all of the edges are there. So now this entire blue region will be replaced by a set of constraints, right? So we'll have, so if we consider this one as these inputs as variables x1, x2, and let's say that this final output is y2, right? So this entire thing will be replaced by some constraints of the form y2 is L1 x1 plus L2 x2 plus L0 and this is again less than u1x1 plus u2x2 plus u0, right? So this entire complex region that we had with multiple intermediate neurons and multiple edges and so on, this entire thing now gets replaced with just this set of two constraints that we have, right? And that leads to a more abstract network. So is the abstraction over here clear? So right now in this more abstract network, what you have is you're dropping all of the constraints corresponding to these edges. You're dropping all of the ReLU constraints corresponding to here. In fact, you're even dropping all of those variables as far as this one is concerned. And you're dropping all of the constraints corresponding to these edges. And instead, you're adding a constraint that looks like this. So remember that all the edges, all the other edges for all the other nodes are here. So if you had an edge going like this, you will still have this neuron and an edge going like this, but just that this edge is now deleted, right?
Yeah.
I'm very sorry, but could you just again quickly explain what we have to do from the beginning?
Yeah, sure. So the basic idea is going to be that we are trying to sort of going by the theme of trying to find relations between neurons and over approximations that will give us relations between neurons. We're trying to look at whole regions of the network and seeing if we can approximate that entire region using just two linear upper and lower bounds, similar to what we do for a single activation function in something in deep poly, right? So remember, in deep poly, we do this sort of a thing in a single activation function, right? So in deep poly, we would usually replace, say, just this part of the network with some linear upper and lower bounds, right?
Okay.
But here, what we're saying is that let's do something else. Let's actually take a whole region of the network and consider that to be one function, kind of like an activation function, right? So if I consider this blue region, see, this is just a function from R2 to R, right? Why? Because it's got two inputs over here, one output over here, right? And then the idea is going to be that, okay, we can consider this entire thing as sort of an R2 to R quote unquote activation function. And for this entire thing, we can come up with a set of linear upper and lower bounds.
Yeah, I guess I don't know. I guess the question might have been that what do you gain by doing this? Okay, because this one, when you replace this entire blue region with some, like you said, upper bounds, I mean, you are abstract. Okay, this would be a coarser abstraction over and above what deep poly would have done, right? For each of those.
So I'm getting an under and over approximation basically.
There is no under approximation. All of it is over approximation.
Oh, okay.
Yeah, so, but this is also an over approximation. But if you replace, say, suppose you ran deep poly. This is a question of clarification that I'm trying to pose. So suppose I ran deep poly, or the Linsim, like, I mean, deep poly. Right now we're only talking about deep poly. Okay, on all things, it will derive lower and upper bound for each node. Okay, at every layer.
Right.
Now, what you're suggesting is just apply the deep poly, run the deep poly on this blue part of your network, okay, to derive some relation on its input-output, as you have shown in the green thing.
Right.
After that, if you did deep poly on this, then it would be, what would that be? That would be even a less precise abstraction than what
right, got it.
Deep poly would be doing. It would be, I guess, now.
Yeah. So and I think that is a very I think that is an interesting question. I think it might actually go both ways. So one of the reasons why this might be more coarse is because we are replacing a lot of constraints by a single linear constraint, right?
Yeah.
But deep poly is also doing that ultimately. One of the things that we may hopefully be able to keep track of that deep poly may not be is the relations between these inputs in a much more direct way. Because
between these inputs and what?
And this output, yeah. Because with deep poly, those relations will be sort of
lost.
No, they won't be lost, but they will be factor. So all of the relations that are encoded by these edges, they'll go through up until this point. But then you have sort of for each one of these ReLUs, the output of the ReLU is only related to the input of the ReLU, right? So all of the relations between these inputs will be factored through the constraints or the abstract constraints of the ReLUs, which don't actually keep track of the relations between the inputs, right? So in particular, or in some sense, if we have, say, these are my two inputs, and this is I'm just drawing a magnified version of whatever I drew before. So the linear upper and lower bounds for each one of these neurons with deep poly is going to be some function of this. But the upper and lower bound that we derive for this neuron, on the other hand, is just a function of this, right? We only get a function of this by composing it with the light green relations that we have, right? So now any relation that were there, for example, between these two neurons, because these two are together related by some linear relations, right? So that gets factored through a set of relations where only this is related to this and only this is related to this. So in that sense, there is a chance that there are some relations that are getting lost.
I don't understand how these two are the one that you've included. I mean, how would they get related at all?
Which two would get related at all?
The one that you have shown here.
So is it these two?
Yeah.
Yeah. So these two are related because at the end of the day, this is going to be given by some function of these two, right? This is also going to be some function of these two.
Yeah.
And so since they both are implicitly dependent on a function of these two, they are going to get implicitly related.
Yeah, but that is true of whether you in the original run of deep poly on the entire network or what you're suggesting. So what is it that?
Yeah. So far, deep poly and what I'm suggesting is going to be the same.
Okay.
But now what deep poly would do is deep poly would then, to get a relationship, the only way deep poly can show a relationship between these two is by getting a relationship between these two and a relationship between these two, and then composing it with the relationship between these two, right? Whereas what we are trying to do is we are trying to look at the relationship between these two directly, right? Because when we finally say that, okay, there is this one output, sort of neuron that is going to be the output of an activation function, we are looking at this entire picture together, right? But deep poly is doing it in a more compositional way, in the sense that deep poly firstly is deriving something that is like a relation between these three. Then it's composing it with these relations, right? And that gives it some implied relation between these three. And that finally will give us some relation, some bound on this, right? But because deep poly is going through these individual relations in the neurons, any relation that was something like this is going to only be captured, or it's actually going to get lost in deep poly, right? Whereas since we are looking at this entire group in its totality, that relation will not get lost. So does that make sense?
I still have one question. So if you can go up.
Yeah.
Questions have to come from them as well. This is good that we're discussing together. Now, are you saying that, okay, you run deep poly on that sub network that you will get?
No. The sub network, I'm going to encode and sort of run something like Linsin on it.
You will run it on Linsin, fine. And then you will get this. Then you will replace that sub-region by this network, right? By this.
Yeah, by
and
this.
how do you use that? How do you use that on this whole thing?
Right. So now what we have is, now we have a simpler set of constraints, right? Some of my ReLU constraints are gone. Some of my linear constraints are gone.
So your network is smaller. Okay.
So my network is smaller. Yeah.
Nodes. And then, so the intention is you use this new network, a smaller network, to do the same verification.
Yeah, we'll use the smaller network to run the same verification.
Yeah, but will this smaller network be, if it is more abstract, it will be more abstract than the earlier one. But that's what you're not saying exactly. Okay, is this over approximation of the original thing, or I guess
no, it is an over approximation of the original network. So this smaller network is definitely an over approximation of this concrete network.
Yeah,
it's definitely an over approximation of this.
But you're saying that it may give, even with that over approximation, it may give better bounds
than deep poly potentially. Yeah.
That's interesting. Why would it? I mean, because of the way that it shows some relationship that is not shown earlier.
Yeah.
Yeah, I got it.
Okay.
Thanks.
Yeah. So, okay, so basically now, once you have sort of this simpler network, then what we can do is we can then basically encode this entire thing, and you can either run deep poly on it, because deep poly is something that can be run on this as well, or we can even run ReLUplex on it. And the benefit of running ReLUplex is basically it gives us a spectrum that will go from the fully defined network to the fully abstract network. And I'll explain what I mean by that.
Yeah, but in order to get this on the smaller one, you're running Linsin with deep poly, correct?
Yeah. So in order to get these bounds, we're going to run Linsin.
Yeah, but after that, you could still be running Linsin or just deep poly. You have a choice, no?
No, we don't need to run Linsin anymore. So after that, all we need to do is we need to either run deep poly, or we can even directly run ReLUplex always. So we have a choice in that respect.
But why not Linsin? Because there's still other parts of this network.
Yeah. So I've shown it here just for example's sake with only one group gone, or one group abstracted out. But ideally, what we would like to do is we would like to abstract multiple groups of neurons, right? So I'm going to show that in a second. So now let's suppose that how would this same algorithm look like if we're abstracting multiple groups of neurons, right? So let's again suppose that we have some network that looks like this. Let's say something like this, right? So now let's say that we decide that we're going to abstract away. So we decide that this is a group of neurons that we are comfortable with abstracting away. This is a group of neurons that we're comfortable in abstracting away. And let's say that finally, this is a group of neurons that we're comfortable with abstracting, right? So then for each one of these groups, or in fact, let's have one of these groups span 3 things. So let's say this is a group. This is another group. And this is the third group, right? So now for each one of these groups, what we have essentially is we have each one of these groups are some functions from, in general, from Rn to Rm, right? So for example, over here, this is going to look like a function from R2 to R3, right? What we're going to do is we're going to run something like linsin on each part that looks like this. So we have one part like this. On this, we will run linsin, and we'll get a bounds on this variable in terms of these inputs. Similarly, we'll have another part for this. On this, we will run linsin and get bounds on this variable in terms of these inputs, and so on, right? And we do these for each one of these groups. So then what happens is, all of these, and just to be clear, the ReLU constraints are always contained within the groups. So all of the ReLU constraints are now gone, and what we are left with is basically going to look like linear bounds on these inputs or on these variables in terms of these inputs, right? So we have a bunch of linear inequalities relating these to these. We also have a bunch of linear inequalities relating, similarly, we'll also have a bunch of linear inequalities relating these to this, and a bunch of linear inequalities relating this to this, right? And now remember that there are some set of edges that are there across the groups, which we have not abstracted out. So there are edges here, right? And these edges will again give some linear relations between, or linear equations between these variables and these variables. Similarly, we have edges like this, which again give linear relations between these variables and these variables. So once we have abstracted it like this, we have converted our entire network into an abstract network consisting of 5 sets of constraints, right? So let's call these 3 groups G1, G2, and G3, let's say. G1, G2, G3. We have some linear inequalities for G1, again, some for G2, some for G3. And we have also some set of edges that we are retaining. So let's call them E1 and E2. And this will give us some equations, right? So we have equations for E1 and E2, right? So these 5 things all together is going to give us the abstract set of constraints for the network. And now all of these sets of constraints that we have, we are going to pass this. And I think the best idea, or at least as the first step, we can try using ReLUplex itself. So we were going to pass this to ReLUplex, have ReLUplex try and verify it. If ReLUplex verifies, then we know that the original network is also safe. If it does not verify, if it comes up with a counterexample, then we have to check for spuriousness and so on, right? So in a high-level overview, there is going to be this sort of several steps in the algorithm. So we are going to take the network and we are going to pass it to a module that is going to create groups, right? And this is going to create these groups of neurons. Which is then we're going to use these groups of neurons. And for each, and it's going to create multiple such groups of neurons, right? So we're going to get something like G1, G2, and so on, up till let's say Gn. And for each one of them, we are going to use Linsin-like algorithm to generate a set of constraints for each one of them, right? Or inequalities, let's say. For G1, for G2, and so on for Gn, right? Then these plus the along with the group of groups, there's also going to be some edges across groups. Which is going to give us some constraints E1 to EM, let's say. All of these will go into, so these form this entire set of constraints, this entire thing is basically going to be our abstract network. And all of this is going to go into ReLUplex. Then ReLUplex, if it produces unsat, then we are done. If it produces sat, then we check for spuriousness. Right? If it is spurious, or if it is not spurious, that is, we have found an actual counterexample, then again we are done. Otherwise, what we'll have to do is we'll have to do some sort of refinement. So we go back to this group create stage and we somehow create different groups to hopefully have lesser number of these abstractions, right? A lesser amount of abstraction. Okay. So this is the sort of high level overview, and then we'll have to sort of go into the details of each one of these spaces. How do we decide which groups to make? How do we, what sort of Linsin-like algorithm do we use, and how can we use ReLUplex, right? This spurious technique is just done by simulating it on the original network. So let's say that this is just simulation on original network. And this is going to give us the sort of framework within which we can try and see if you can verify some difference. Right? Okay, so any questions so far regarding the high level overview? Or the broad intuitive idea of what we're trying to do or planning to do? Sir, does this make sense to you?
I think so. Yes.
Yeah.
I think this. Okay. So far, I don't think they've seen a cigar loop. Okay. Although maybe I did.
Yeah, I think this is the first time that.
Yeah. So
Yeah.
so this cigar, this refinement, extracting counterexample, and so on. I mean, you will. You will see an instance of that in this node merging discussion. Okay.
Right. Yeah. So I don't know if necessarily we'll be able to use the information from the counterexample to refine the groups, but or at least how smartly we will be able to use that.
That's true, because
right.
See, if you want to do that, then you'll have to relate this counterexample to kind of derive some information as to which group that you abstracted into some linear constraints, upper bound and linear constraints. You will have to either replace it Okay, make it into a smaller one or replace it with the original one.
Right.
So yeah, so that relationship, only then it will be counter-example guided. But maybe yeah, I mean, you guys have to yeah, I don't yeah. So what I'm saying is, you will see this flow chart that Diganta has shown here. This is a very general framework called CGAR loop. Okay, CGAR stands for counter example guided refinement. Okay, so far you've only seen ways of abstracting using over approximations. And as you know, the over approximation sometimes gives rise to spurious counter examples. It can say, oh, not verified, but it may not, that may not mean the original network is in violation of that property. Then you will have to refine it. Okay, and you know, hopefully you can use that counter example to guide which part of the network that you abstracted to refine, and how much, and so on and so forth. So this and this is what is called a CGAR loop. Okay, different, you know, regardless of what kind of abstraction method we use and how you choose to refine which parts you use, this overall framework is called CGAR. It can be used with different kinds of abstraction. One such thing I'm going to show you tomorrow, where you will have more details. Okay, so what Diganta and we are proposing for you to do is a new way of doing it by using Linson. Okay, and that is the so question is, are you too confused, or do you get into the overall gist of it?
Yeah, I mean, I feel like I probably didn't do a too good job of explaining it. So it's totally understandable if you're completely confused.
I don't think it's only because of that. This is it's an unfamiliar concept, okay, for them. So the first time, if you don't understand, it is okay. Okay, so and you will have an opportunity to see the CGAR thing, how it works in a different context tomorrow. And if you have any questions, you know, then we can revisit this. Of course, we'll be revisiting. Yeah, to cover the details and so on. Any questions? So we are close to 6, getting closer.
Yeah. I think we'll have to slowly start wrapping up, right?
Yeah. So any questions, guys? I mean, about your new assignments, I mean, project assignment, as well as this overall thing. I mean, it's okay if you will say, "Oh, I'm confused. I don't understand." You can say that too.
So in the assignment,
what's your name?
Rohan.
Who?
Rohan.
Rohan. Ah, okay. Yeah. Yes.
So in the assignment, after choosing one of the DNAs, we have to verify it using Reliplex node abstraction and deep poly. So will we have to implement Reliplex and deep poly from scratch in Python?
No.
Or is there any kind of gap?
Yeah, so Reliplex you don't have to implement. Reliplex is, I think I showed Reliplex is one of the tutorials, right? Yeah, so Reliplex you can just directly use.
Okay.
Yeah, that tutorial is called Marabou tutorial.
Yeah.
Marabou. Yeah.
Yeah.
That's already there in the video. Okay. So that is off the shelf. You can just take it and use it.
Yeah.
Okay.
So is deep poly.
Right. So I think this node merging based thing is off the shelf. Deep poly is not. With the node merging based framework, while it is off the shelf, encoding any new properties into it is hard. And it's the similar sort of situation with deep poly as well, right? So the node merging based framework, we decided that they'll implement, right? So
let's see, because here, okay, because right now, if this is what they're implementing, then there's no node merging thing here. Okay?
Yeah. Then I think what we can maybe...
but implementing node merging is very easy. Okay.
Right.
So I don't think that it is there and that paper has the implementation. What I am a little bit concerned is about implementing the entire deep poly if they have to, the Linson thing, okay, which, yeah. But anyway, going back to your question, Reluplex and even the node, well, the node merging, why do you say you have to implement Diganta? So because Marabou does not, because they do have a code, but you're not sure if that code is so readily usable for the kind of problem issue.
Yeah. So that code is some, it is Dockerized and it's got some hard-coded, like it's got some of these properties hard-coded in this huge Python file, right? So while these existing properties can be used, I don't think that really, like it's impossible to dive into the code and see what's going on, first of all. And second of all, it's not really like extendable or very, like it doesn't really tell you much that if you just run this code, it doesn't really give you much in terms of what's happening, right? So I think that.
Yeah, no, I understand the purpose of the reason that Rohan is asking this question, because since as one of the items in the assignment, we are requiring them to use this node merging on that, and then within 2 weeks, if they have to implement it, will that be too difficult? Is that right, Rohan?
Yeah. So even for deep poly, Diganta said that we might have to do a Python implementation from scratch, and if that's true for node abstraction as well, so that will be a big task.
Correct.
Yeah. So may I suggest something, sir?
Yeah, please.
So I'm saying that let's for this current assignment, let's have a node merging based implementation. As like have them implement node merging. I think node merging is something.
Let's move deep poly completely out.
Yeah. Because even in this loop, I think we can at least initially we can try it with Reluplex, right?
Yeah.
So it's not and then they'll have to implement some things over here as well. So there is enough work here that I think it's okay if we just do the node merging for this kind of assignment.
Okay. But is that realistic? But for them to do it individually, because that's what I said individually. I guess it can be done, huh? In 2 weeks.
Yeah, I think so. I think it should be doable within 2-3 days. But then 2-3 days, I'm saying, not considering other work that people will have. So of course, 2 weeks.
Okay, so you will get a better idea, Rohan and others, when I discuss it tomorrow. That paper has, pseudo code in the paper itself, which I will be showing you. Okay.
Yeah.
So we can, you will get an idea of the level of effort required if you have to implement it. Okay.
Yes. So just to reiterate and clarify, Reluplex is already implemented in Marabou.
Off the shelf. That is off the shelf.
Yeah, that is off the shelf. Just use it and refer to tutorial.
I mean, will they be able to, if they want to, just try the existing code for node merging and then see if it works?
Sure, I think, but the issue is the existing code will definitely work for all of the properties of the ECAS-XU DNNs.
Because they have already run on that. Yeah.
Right. But the issue is that if you want to add any more properties, right?
Correct.
You have to really dive into the code. It's all hard coded in one particular Python file, right?
It only works for that property is the way that they have.
Yeah. And they have hard coded all of these 10 properties manually in their code. So that effort needs to be done. And of course, it's for that one has to understand what's going on inside the code to some level. In my experience, the effort required to do that is the same as the effort required to just re-implement it from scratch. And a lot of the things when they'll implement the things like, reading NNet files and so on, those things will translate to both the project and other parts of the assignment as well. So that is why I'm saying that for deep poly,
Yes.
yeah, so do an implementation from scratch in Python.
Yeah, for deep poly, certainly. Okay. Now the question is, for
So not for deep poly. I'm saying for
for
the
known merging.
merge. Yeah.
So let's revisit this tomorrow. Okay. And,
yeah, sure.
After I present it, we'll have you'll get an idea, and you can take a call. Yeah.
Yeah. And like I was saying, like I think that this should be easy, but then you guys are going to see the merge based abstraction algorithm tomorrow. So then you guys can decide if it is too complicated or too simple for implementation using NumPy.
Okay.
Yeah. And then this will be it. So there is let's deep poly, let's say that we are not going to worry about it right now.
Yes. Okay, so tomorrow it will be at 3:30 and in person. Okay, so I'll have to get a lecture hall. I'll see if I can get the main seminar room, but it's kind of highly unlikely, I think, because although that seminar room is too big for us, it can, that is one place where I can roam around, but still be able to get the audio recorded, for people that want to follow on a Zoom link. Okay, which is important. So I'll try to get that Zoom link somehow working as well, because Diganta, I want you to join. Okay.
Yeah, I'll be there.
And Sudakshina is keen as well. So
so this is tomorrow at 3:30, right?
Correct. Yes.
Yeah, I'll be there.
Okay. So if there are no more questions, there any more questions?
So if there are no more questions, I do I want you to sort of spend, and if you have some time, thinking about these two pieces at least. Like, how can you sort of choose which groups to join together? Given a group, how can you, is it just a direct application of Linsin to just get these linear upper and lower bounds for the group? And once you have all of these constraints, is it something that Reluplex can handle? Right. So I think these three things start thinking about this or turning it in your minds a little bit, I guess.
Decided on your partners? If so,
should we have two groups too, or
one?
No. So was it decided that we should have groups of two, or?
Correct, groups of two, and I'll work separately with Nabeen. Okay.
Right.
So we'll have a plan. So just a group. Yeah, you'll be working in pairs. Yes.
So I think, sir, tomorrow we'll let you know the groups.
Okay.
When we meet in person.
Yeah, you can send it by email. Okay.